Hey everyone, I'm Harkrishn Patro. I'm a software engineer at AWS and one of the maintainers for the Valkey project. Today I'll be talking about Valkey clustering. How does it work internally? So first I'll go through the overview of the project, the recent work we have done in the community, and then I'll talk about how do we deploy Valkey in production, the different modes, and then we'll go do a deep dive into clustering. So Valkey is an in-memory key value store, which has been forked from open source Redis back in March 2024. Its primary use case is to handle caching, but lots of modern web applications use it for lots of different use cases like leaderboard management, session store, you name it, like there is message brokering and like lots of cool stuff. So like I mentioned, Valkey has been forked from Redis OS 7.2 and it is fully compatible with that. So it's pretty easy to migrate from Redis to Valkey. It's backed by the Linux Foundation, so it's free, open source, and it's going to stay that. And it has been built by the community members, so there are active contributors from all over the world, and there are like more than 200 active contributors to the project, and it's growing, so feel free to join the community. So brief history is Redis chose to change the license from open source to sourceable back in March 2024. And then the community members decided that we need an open source alternative to it. And then we decided to fork it. And since then, we have released 3 major minor versions. Recently, Valkey 8.1 was released in April 2025. So the recent work which we have done in the community is around memory efficiency in IO threads. So any key value store which is built on top of memory looks into those 2 key pillars, which is memory overhead reduction and having a high throughput. So for memory efficiency, what we have done is we realized that we want to provide the users to store as much data as much as possible and looked into ways to optimize that. And the key insight was like there was a lot of pointers which was taking lots of memory overhead per key value pair. And the idea was to pack in data all together into a single block of memory and reduce the overhead. And with Valkey 8.0 and 8.1, we're able to improve or reduce 20% memory utilization per release. This also helped with avoiding pointer chasing, where you are basically assessing random memory addresses, which doesn't help a lot with you're basically thrashing the L1 cache of the CPU. So rather you try to assess the data altogether and bring in the key value pair into the CPU cache and make it more performant. The other aspect, which is the throughput. So Valkey is a single threaded process and all of the command processing happens through the event loop. But we realized that more than 50% of the CPU cycles gets used for the IO part of the operation. And the key idea was to offload that IO input-output operations to a separate thread. And with that, we are also able to batch lots of key value pair operations together and perform memory prefetching. This is again going back to the same idea that if you can get the data to the L1, L2 cache of the CPU, you get more performance. And with the IO thread, we are able to serialize or deserialize the command which is received by the server. And then we are able to build the command to be handled by the main thread. And once the command is ready to be processed, we pass it on to the main thread. Once the main thread processes it, which is pretty fast, it offloads the response back to the IO thread, which takes the response, builds it, and passes it on to the TCP socket. Beyond that, we have been also looking at improving the cluster process, where we want it to be more stable, run larger clusters at ease. And throughout the releases, we have improved lots of different aspects of clustering. There are also lots of new data structures which have been introduced in the community, JSON and Bloom being one of the most requested data structures. Vector similarity search is the buzz in the town, so that has also been added to the community. Looking at some of the numbers, recently one of the community members from Momento benchmarked Valkey 8.1 and Redis 8.0 and discovered that Valkey is able to handle more than 1 million RPS on a CHG to XL large AWS instance for sets, and gets are also in line with that. This is quite a lot of improvements since Redis 7.2 and Valkey 7.2, where we have almost tripled the performance. Redis has around 750K throughput for set operations. Now going into how Valkey gets deployed in production, the first one which came out was Valkey standalone. Over here, there's one primary and multiple replicas of it. So that means that all of the writes goes to the primary and it gets replicated to the replicas. And it's based off eventual consistency. So the data gets returned to the primary, and at some point in future, the data would show up in replica. This way, if you want to scale reads, which is one of the primary use case of a caching system, that you're reading pretty fast from the server, so you can scale reads easily. However, the ease to set up these 4 nodes of primary replica, there are challenges which would show up once you want to scale. The key challenge which I see is, if the primary goes down, there is no inbuilt mechanism for it to fail over, for a replica to fail over to become the primary. And this kind of makes a pain for operators to run Valkey, and you would need dependency on some third-party system to make it more fault tolerant. There are also use cases where users wants to store more key value in a single box, or if it has reached the ceiling of a vertical node size, you want to store more, but there is no other mode. And like Valkey is single-threaded, and IO threading can scale up to only a certain extent. Write throughput also bottlenecks at some point. Hence, Valkey Cluster was introduced. So the primary idea is to provide horizontal scaling linearly. And the idea is to make the setup pretty simple so that there is no tiered deployment structure. So all of the nodes are basically the same piece of software. There is also inbuilt mechanism of data sharding. And there are pieces which ties together, which is like handling any kind of clients connecting to the wrong node and getting redirections to the appropriate node. Also, like I mentioned, the drawback in Valkey standalone, that is fault tolerance is inbuilt into Valkey cluster. So if a replica goes, or primary goes down, replica becomes the leader of that particular shard, and data write still goes on. So in order to build a cluster, we need 3 different pieces to handle this decentralized architecture. The first is the node itself. The second is way to shard data across the nodes. And the third is some form of intercommunication between these nodes, which we call it cluster bus. So let's look into cluster node. So cluster node is basically the same standalone server which is able to handle any kind of read-write traffic. Beyond that, it has few other things along with it. That is, in order to detect failures, we need to have some kind of heartbeat mechanism built into the node. The third being, we need to be able to point the clients to the right node to handle the traffic. So cluster node has 2 modes of operation. This is in line with the data serving part, where the primary node, which is serving writes, becomes a voting member. So the primaries altogether form the quorum. And the replica is kind of a standby, where if a primary goes down, it becomes a candidate and gets promoted to a primary and becomes part of the quorum again. Regarding the data sharding, cluster slots is a concept which is unique to Valkey. where a key gets mapped to a slot and slot gets mapped to a node. This is pretty trivial, but helps with the data distribution, where there are at the max 16,384 slots in the cluster. So the slots would be assigned to some of the primary nodes, and the way the key gets distributed is you take a CR16 hash of the key and modulo it by 16,384. The primary are the owners of the slots. The replica basically follows the primary for any of the information. The last piece of the puzzle is cluster bus. So the nodes we discussed about needs to have some form of communication between each other. So we have introduced bidirectional TCP connections for them to interact with each other. Each node connects to all other nodes in the system. So when the cluster converges all together, there's a mesh topology where everyone is connected to all other nodes. There is a custom message protocol for Valkey through which two nodes communicate with each other and they understand them. There are also some interesting parts to the message which gets transferred, which is gossip. So basically you inform other nodes about some other node that this node is healthy or this node is down. We also use it or repurpose the cluster bus for pub/sub traffic, and pub/sub is one of the use case which is heavily used in Valkey, where you have a publisher subscriber and do a basically message passing between each other. So cluster bus supports multiple different kinds of data to be transferred. The most important ones are meet, ping, and pong. So meet is basically when you have to discover some other node, you use a meet packet. Ping and pong is basically heartbeat of a node to other. And there are other scenarios which are one-off, but if there is a node failure, we need to broadcast to other nodes that, hey, this node has failed. Or if this node is healthy, we need to update them. Like I mentioned, pub/sub traffic goes through it. So we have a message type of pub/sub and pub/sub shard to support it. So let's briefly look into the message header format of cluster bus. There are lots of different variables, but we don't need to focus on it on each individual. The key idea is we want to send the sender information as part of the packet so that the node receiving it would try to connect to it or discover it through the sender name. Sender name is unique to each node, and that's how they discover each other. There are also parts where if you are a replica of some node, then primary information would be part of replica of field. And there are IP and port for a node to connect to. There is, at the end of the payload, a message type specific. Hey. So over the TCP socket, we need to send in some kind of message between two nodes to be able to. So I'll talk through the use cases where cluster bus is used just after this. Maybe that would help you understand the use case for cluster bus. Going back to the cluster bus format, there is an arbitrary payload at the end of the message, which is dictated by the type. So we'll look into how ping, pong, and meet share additional information as part of the packet. So the fixed message header is around 2 kilobytes, and in a meet and a ping on pong packet, what we add is basically an array of gossip messages. The gossip message in itself is 100 bytes, but this really helps us in reducing traffic being sent from one node to all other nodes, where if you are able to share information about subset of nodes, then the other node doesn't need to talk to that node to discover if they are healthy or not. So here we would be sharing the node name, the time when it was healthy, the IP and port, and so on, so that the cluster bus traffic is pretty low. So in order to tie all this thread, I'll go through how these three components gets utilized, and we're able to build a membership, How do we handle the redirections? How do we detect failures? Then after the failure detection, how do we handle failover? And at the end, I'll go through if there is a conflict, how do we handle it? So once the node has been set up, how do they communicate with each other? So let's say I have an example of 6 nodes, 3 primary and 3 replicas. The possible mechanism is you connect one node to all other nodes and do that same thing all over. That would be order of n square, which would be quite time consuming for an operator to establish all these connections. So what Valkey provides you is a way to reduce some of these operations where you just connect one node to all other nodes and let the gossip take over. So over here, I'm establishing connection from P1 to all other nodes, where P1 connects to P2, P3, R1, R2, and R3. Now, once the base has been set up, that is one node connected to all other nodes, P1 would start gossiping about other nodes in the cluster to some of the nodes it has discovered. So in this case, we see P1 gossips about P3 and R1 to P2, and about P2 and R3 with P3. So this is part of the packet which I showcased as part of the cluster bus, where it would be sharing some additional information. Once P2 and P3 discover these other nodes, they would establish this bidirectional links between each other. Now part of the topology has been formed through gossip, and the process continues, and within a very short span of time, all nodes would be connected to each other. And this is the full convergence, and all the nodes are aware of other nodes and have the same view. Once that is out of the picture, how does a client work with this decentralized cluster nodes? So initially, a client would connect to some random node and perform any kind of operations. In this example, I'm talking about 3 primaries being in picture, and each have 2 replicas. So the client here connects to primary 1 and performs a set operation, set foo and bar. Foo is the key and bar is the value. And the slot which has been assigned to each of these primary or the shards, basically primary 1 has slot 0 to 5460, primary 2 has 5461 to 10,922, and the remaining is with primary 3. So if you perform a CRC16 and modulo it by 16,384 for foo, you would get the slot number as 12,182, which clearly doesn't line up with primary 1 slot ownership. And now what primary 1 would do, that it is already aware that it doesn't have the slot and is aware primary 3 has that slot. It would send a redirection which is moved 12182 to primary 3. Basically, it's indicating the client that you are on the wrong node for this particular key, go connect to primary 3. And the client will be smart enough to connect to the appropriate node and send the set foo bar again, and the operation succeeds. The client would ideally cache this information so that they don't do this redirection all the time. It only needs to refresh the topology if there is a change in the structure of the cluster setup. So now coming to the most interesting part as per me, which is the failure detection. Failure detection is key to the cluster, where the primary node going down is quite painful for the application developers. So we need to detect that fast and act on it. The 2 key aspect to it is ping sent and pong receive. This is basically you sending a message to someone and expecting a response back within a certain period of time. So once ping sent has been done and pong received hasn't been received within a period which is call it as node timeout, if it doesn't send a response back within half of it, we think that it has partially failed, at least as per our view. Then once the time elapses for entire node timeout and other nodes also have the same view that this node is no longer responsive, we mark it as failed. This time is pretty configurable, and the operators can choose a time as per their environment. The default is 15 seconds. So let's look at, hey, so while this was built, Raft was still not in picture. And the other aspect is it's pretty easier to maintain. There is no file storage involved with this architecture. The third piece is I tried exploring Raft for this particular Valkey clustering setup. There are challenges which you have to have a tiered architecture where there has to be a certain number of Raft nodes, and then there could be a Valkey set of nodes. If you introduce Raft within Valkey, and if you have all the nodes handling Raft, it becomes quite chatty and quite expensive to handle Raft. Decentralized architecture scales pretty well to a certain extent, and till now we have been able to handle that, the demand basically from the application side. I'll talk about the benchmarking at the end of the talk. Yeah. Sorry? No, it has a basically a tie-up. Like I mentioned, primaries become the leader. So that's pretty much the concept. There is no election as such. If the node is a primary, it is also the leader for voting mechanisms. Cool. So I'll move on to the basically how failure detection works in Valkey. So at any point in time, each node sends a message or a ping to other node at every second interval, and also ensures that it sends a message within node timeout by 2. Yeah. Yeah. So this is a shard. I've just put a box to indicate that they're, yeah. So N1 here is a single node. So I'm just trying to showcase, so at least from the diagram on the right side, each node is unique to, so primary has ownership of the slots. They could have one or more slots. Replicas basically follow the primary blindly. Like they don't have any say in terms of slot ownership. Mhm. N1 is a single node. I'm just trying to showcase the failure detection mechanism. Slots do not have any role in the failure detection. You could think that like each individual here is talking to each other and trying to detect if they are responding back or not. So coming back to this image, there are 3 nodes, and in an idle healthy state, each node would be sending a message to other node at every second. And we also ensure that within 7.5 seconds, or basically the default is node timeout by 2, we send out a ping message to the other node and expect a response back. So here, if you take a look at this most basic use case, node 1 sends a ping to node 2, and node 2 responds back with a pong, but it also piggybacks some additional information that node 3 is also healthy. Similarly, node 3 had sent a message earlier on to node 2 with a ping, and node 2 responded back with a pong. So node 2 is aware that both node 1 and node 2 are healthy and can exchange some message and some additional information with the other nodes. I'll move on to some of the use case or some of the cases where some failure happens. So yeah, go ahead. So it won't send a message, like it will still do some message arbitrarily at every second. But even if it has received some message about node 3 health, then it won't send for a period of node timeout by 2 because it has discovered that it is healthy. So in a real world setup, if it has received a message within the node timeout by 2 period, it doesn't need to send a message to the other node. So that is taken care of in Valkey. Is there any other question? Cool. I'll talk about the failure scenarios. So there are two kind of scenarios. One is partial failure, where the clients are still able to like basically perform read and write operations from the node, but there could be some intercommunication issue between this node itself. In this view, the application is still able to handle all of its traffic, and there is no issue as such. But N2 is not able to connect to N1 due to some network glitch, and N1 is trying to send a ping to N2 and is not receiving a pong back. However, N3 here, the node is active and able to communicate with N1 and N2. So as per that node's view, both of these nodes are healthy. I'll show what happens internally. Basically, like I mentioned, ping sent and pong received are the two variables which are maintained inside the cluster state. So over here, if you see, each node has these two variables for all other nodes. So N1 has a view of N2 where ping was sent but pong was not received. But for N3, it has a timestamp attached to it, T2 and T3. Similarly, for both the other nodes, there's a data associated to each node. From N2's view, N1 has, like, we have not been able to send a message to N1, and neither we have received any. So the problem is that, do we trigger a failure and mark the node as failed and do a failover? That would be bad for the application because there is nothing wrong in that from the application point of view. So what we do first is we try to re-establish the link, basically try to disconnect it and re-establish a TCP link. And if it goes through and the message passing happens after that, then the node is marked as healthy and there is no further operations happening on it in terms of failure and failover. But let's take an example where there is some actual issue happening to the node and how do we deal with it. So over here, I have created a partition where node N1 is no longer reachable to node N2 and N3. So like I mentioned, first Valkey would try to disconnect and try to reconnect. In this case, the node reconnection doesn't work. So N2 and N3 do not have any active link. So they would talk to, N2 and N3 would talk with each other and share their view that, hey, I see that node N1 is partially failed as per my view. Similarly, N3 would send a pong back and say that I also have the same view, that N1 is no longer reachable. So all these nodes are primary, then they would be able to form a quorum within themselves and see that we have received enough information from the primaries that this node is no longer reachable. This activity can be taken up by any of the node if it has received enough partial failure reports. And over here, N2 detects that it has received enough messages about N1's partial failure and marks the node N1 as failed. Once that node has been marked as failed, we want to broadcast this information to all other nodes so that they are aware that this node has failed and mark it on their side as well. So here we broadcast it to all other nodes. Now going to the next section, where what do you do with this failure detection? Once the node has been marked as failed, how do we act upon it? And that's where replicas come into the picture. So if a primary node has failed or partitioned away, like in our previous example, the set of next steps which would happen is the link disconnection would happen again. And then what would happen is a replica, being an election candidate, it could ask that, hey, I'm still healthy. I can be a owner for this particular shard. Please take in my request and prove this. This vote request goes to all the primaries in the cluster and they take a decision if they want to approve it or not. Over here, like I have already mentioned, there are 3 primaries and 3 replicas. One primary is down, but there are still 2 active primaries who can take the decision. So P2 and P3 receive this voting request and they see that P1 is down and R1 is healthy, so it could be promoted. and they approve the request. Once R1 receives that it has been approved, it would promote itself to become the primary of that shard, and it will be able to serve write traffic. The next part would be, what if P1 comes back? Once P1 is back, it is also acting as a primary of that particular shard and isn't aware of the view of the cluster which has happened since it was down. So it stays in a fenced manner that it is not serving any traffic at that point of time, and try to reconcile the view from the cluster. And once it establishes all the connections to other nodes and receives information that what is the current view of the cluster, it is able to demote itself to a replica and serve read traffic for that particular shard. After the failover is done, let's look into a use case where there is some conflict. Like I mentioned, there is at a given point in time there could be multiple primaries for a given shard, and how do we deal with it? For that, what Valkey has is something called epoch values. This is where it takes cue from, or at least the idea is pretty similar to Raf's term, where if any new activity happens, there is a bump in epoch. Epoch is basically a monotonically increasing counter. So the bigger it is, the more latest the information is. There are two types of epochs in the system. One is the node epoch. Basically, it is the node's counter, and that is the latest view as per that node. And then there is a cluster epoch. This is the maximum across the cluster. And this dictates any kind of new operation which needs to be performed for the cluster, like the promotion of a replica or a slot transfer from one node to other node. Such operations gets the cluster epoch being bumped. I'll talk through this previous example where one node was down and how epoch takes a role in handling the conflict. So over here, P1, P2, P3, R1, R2, R3 have a unique node epoch value. That is, P1 has 1, P2 has 2, P3 has 3, and so on. The maximum epoch value here is 6, so that's the cluster epoch. If while the cluster is being created, if there is a conflict, the node would talk with each other and see that the epoch has conflicted with each other, and one of the node would bump it. That is based on the lexicographic order for that node ID. But eventually, all the nodes would have a unique node ID and epoch value. So now let's go to the replica candidate asking for ownership of that particular shard and slots. And what the primaries do is they see that there has been no other request for this epoch value for any kind of failover operation. So this approval could go through because there has been no change for this particular epoch. So they approve the request for this particular epoch here, which is 6. And R1, after receives the approval, what it does is it performs an epoch bump and promotes itself to become the primary. Once the epoch bump goes through, this needs to be broadcasted to all other nodes so that they know that the max cluster epoch is of 7 now, and no other votes could happen for 6 anymore. Once this information gets broadcasted, it is passed on to all nodes, and they update their topology that R1 is the new primary for that particular shard, and they could handle client redirection correctly again. Once P1 heals again, it comes back and tries to connect to the other nodes like we talked about. But over here, P1 had an epoch value of 1. Even if it was marked as primary of that shard, its epoch value is less than R1. So that's where the tiebreaker happens, that, hey, you have an epoch value which is older than mine, and R1 would push its configurations to P1, and P1 would start replicating from R1. This is very helpful for scenarios where there are multiple failovers happening at a given point in time, and epoch helps with converging to a single view across the cluster. Yeah. Yes. So for split brain scenarios as well, this helps where the the cluster which has a majority of primaries would have a higher epoch, because epoch bump can't happen like we saw in the previous slide where epoch bump happens only once for a particular request. So the side which has more number of primaries, basically forming a quorum, can only bump the epoch. And once they converge to a single view, the minority would discover that they were not able to bump any kind of epoch and converge to a single view across the cluster. It's peer-to-peer. Each node communicates with all other nodes. So, so the shard could have one or more node. So if it has only one node, then it can't have any of these health detection mechanism. So for scenarios where your cluster or a shard doesn't have enough node to take these actions, it helps to have it across the cluster. There is general deployment of one primary and one replica, which is not enough to handle these kind of failure scenarios like we talked in the standalone mode. So it needs to have third-party view and handle these failure detection and failover. Yeah, if all the node goes down due to some reason, which is not common or I haven't seen in production. Mm-hmm. Sure. Yeah, that's true. So there won't be any, that's a pretty good question where, so the question is like, what if the primary and replica, none of them are able to communicate with any other nodes in the shard? What happens? In that case, that particular slots are no longer available for write or read traffic, but there's no slot movement happening for that particular shard. And basically, operator should ideally check in to see why the entire shard is down, or the operator could perform a manual slot movement from those particular nodes to the other nodes to able to handle traffic. That is generally done for scaling kind of operation where you want to reduce the number of nodes in the cluster, but it is done in a phased manner where you move the slots first to be able to still serving the write traffic and read traffic, and then terminate these instances. So you could take snapshots, which is called RDB in Valkey. You could take that snapshot if the node is still available and load it to some other node. We term that mechanism as slot migration, where you move data from one node to other node. Basically, you could do it over disk and then take it over network, or it can be done over the network entirely. Cool. All right. The last part is, does this scale well? This is the question which has been asked around Valkey and Redis, that does this scale well? And since last 2 years, I've been improving the Valkey cluster to be able to perform better and take up more number of nodes in the cluster itself. However, this was never benchmarked on like how much can it scale, what's the message transfer rate between these nodes and the entire cluster, and how does failover work when there are multiple failures. Like in a cloud environment, there could be an AZ failure kind of situation where half or 1/3 of the node goes down. How does the failover work? And the key part is, don't say that it doesn't scale well, rather measure it and then see what needs to be improved. And that was the goal behind the project I was working on. And I realized that as part of the process, it could scale really well up to 2000 nodes. This was kind of a eye-opener for all of us, where the current limit or the major production players kind of scale up to 500 nodes, which would be a 4x jump in terms of the cluster size and can serve more traffic from a single cluster. And you don't need to build in client-side sharding in any of the form. The key part to it is being aware that node timeout shouldn't be reduced much lower than 15 seconds, because it could bring in scenarios where some message didn't get transferred and you do incorrect failovers, which are like false positives. The other aspect which is critical for a lot of people who run databases and caches is like, how long was my outage? And for scenarios, for one failover kind of thing, it's much less than 10 seconds. And with almost 10% of the node failing, it takes around 20 seconds. For 1/3 of the nodes going down, it takes around 60 seconds. Yes. So this was done on AWS US East 1 with it being randomly assigned to random AZs. So I think there were 6 AZs in picture, and like we didn't artificially force them into one particular AZ. The key idea is that we want it to be as distributed as possible to avoid any kind of failure for a particular AZ, which can happen in cloud at any point. Yeah. So the setup is 1 primary and 2 replicas. So there were 666 voting nodes or 666 primaries. And this is a configuration which we recommend, that you have 1 primary and 2 replicas, so that in any case there are applications been deployed across multiple AZs, you have a low latency to read from that particular AZ from Valkey nodes. So if you reduce it much lower, let's say we take 5 seconds, we need to finish all the pings and pongs within 2.5 seconds. And that could be a huge increase in terms of message size and message count. Every 1 second, we pick one random node to communicate to, but within the node timeout by 2, we communicate with all other nodes. So if we don't receive gossip information about other nodes, or due to some reason we haven't received enough information, we'll reach out to all nodes to receive their health status. That's the peer status. Sorry, give me a second. Which one? 10% node failure detection? Yeah, that's a pretty good question. So once the failure has been detected and we need to perform failover, because of the epoch value, only one failover can be performed per epoch. So we need to serialize all of the failover one after another. And we need to take into account, like in this case, we need to take account at least 334 votes to confirm that this failover can go through. So all of this happens serially, and within 5 to 6 seconds, it was able to handle 200 or over here 10% node is like 10% of the primaries. So it was able to handle the size of the, I think it's roughly 33 nodes. I have benchmarked for, let's say, half of the n by 2 minus 1 nodes going down, and it does happen within 60 seconds to handle like almost half of your cluster going down. That's one of the biggest challenge when something goes down to, or something happens in a cluster, why they are not converging. So that's one of the key areas which I'm currently looking at. Like, the current way of thing doesn't help to debug a 2000 nodes cluster. So we are building mechanisms where information gets logged correctly. So I'll take a small example where we're logging partial failure for all primaries, saying that, hey, this node has partially failed. And in this scenario, if 666 nodes are saying that, hey, I see it has partially failed, we are logging it at a pretty fast rate, and it is causing 100% CPU utilization just because we are logging so much on the nodes. So key is we are trying to introduce new metrics. Some of it is here, which will show up in 9.0, that we capture those small, like let's say p fail, primary fail, and such scenarios. We're able to put it as part of the cluster info metrics, and other third-party system can pull that data. As well as we're changing the logging mechanism where we shouldn't log irrelevant information. Basically, the view of all 2000 nodes cluster doesn't needs to be logged. Rather, you log or snapshot of the view of the node at some point, like it can be configured, so that once you go back, you see how it has changed over the period of time and able to build a lineage of information. Mm-hmm. Sure. That is where I feel so there's no open source solution to it, but one of my colleagues had built a way to merge in all the logs and get a unified view. Maybe at some point he would open source it, but to each their own kind of thing is at play at this point. But it's a pretty fair point that being able to form a view and then able to take action on it is quite challenging at this point. Just to quickly go back to the results, this was possible with a 2.2% CPU utilization in idle state, and the throughput was around 2 Mbps. All right, that was pretty much about the Valkey clustering system. The next part, which is kind of very interesting, is how do we make sure that we are able to provide a reliable mechanism to handle this cluster, like Mallikarjun mentioned. So that's the ongoing work where large and more stable clusters run easily and you're able to debug it. Further from that, we're also introducing new features, which is like sub key level expiries, which is kind of a big ask where people use hashes and want to do expiry on top of it. There is also some gaps in terms of moving from standalone to cluster, which is like multiple databases, where they run it as a multi-tenant system and cluster doesn't allow multi-databases. So we're adding support for that in Valkey 9. And search has been a big ask from the community. So we're building it. It will be in production maybe in a year or two. Feel free to join in the community. It's completely free and open source. So there are a lot of interesting issues and PRs already in the community. So feel free to check it out. All right, that's my time. Thank you everyone for joining in and listening.